Thanks to the organizers for giving me a chance to speak about the role of drag and gravity in a gravitationally unstable disk. So first, let's start with a short introduction on what is a gravitationally unstable disk. So in the U, a disk can be a disk mass can be comparable to its host star, and so when a disk is about 10% of the host star or higher, the disk can develop gravitational instabilities, like in the form of large-scale spiral structures, as you can see on the image on the right. So, on the way of finding out when a disk is gravitationally unstable is with the atomic Q parameter. So it depends on the sound speed of the disk and the gas surface density. So when a disk is either cold or massive or both, a disk becomes gravitationally unstable. When we look at the brightest disks in observations from ALMA, we see that a large majority of this are symmetric with ring and gap structure. A massive disk, as I mentioned, is expected to harbor a large-scale spiral structures, and although they're not seen as frequently, we do see some examples of them, as the ones highlighted here. In the disks with ring and gap structures, a common explanation for their origin are planets.
Recording in progress.
Since any planet that forms would interact with the disk as they exert a force on each other, and the exchange of angular momentum between the planet and the disk can lead to planet migration. But if a planet is massive enough, it can open up a gap, as seen here. Evidence for planets have been strengthened by observations of the gas kinematics. So shown here is a specific channel map of CO in a perfectly Keplerian disk. These channel maps here, these rings here would be smooth and continuous. However, in this disk here, it has ring and gap structure, as you might be able to see from the continuum in the background, and in the gap you can see a kink on one side of the disk, and that is a signature of a planet in the kinematics. And here's what the what the disk looks like in the continuum. So you can see that the kink lies in the gap, as we would expect. So from the gaps and widths in the continuum and the kinks in the kinematics, we can infer the masses and locations of these potential planets, and those are shown in blue. And a lot of these planets are around a Jupiter mass at tens of AU to a couple hundred AU. And when we look at the ages of these disks, which are a little uncertain, we see that many of the disks which have rings and gaps are quite young. Even disks younger than 1 million years old still show ring and gap structure. This in combination with the masses and locations of the planets, can pose a problem for traditional planet formation models like co-accretion. So as you can see in this image here, it can take a few million years for a Jupiter-like planet to form at 5 AU, which is a problem if the disk is only a few million years old. And this problem gets worse as most of the inferred planets are much further out, where it takes much longer to build a giant planet as just simply far less material further out. So as this talk is about dust in a gravitational stable disk, I'll mention some important terms for the dust dynamics. So the first one is the drag force, which acts to remove any velocity difference between the dust and the gas. The second is the stopping time, which tells us how fast the drag affects the motion of the dust. And the third is the Stokes number, which is a ratio of the stopping time to the orbital time scale. The important thing here is that the drag force, it depends on the grain size and the velocity difference between the dust and the gas. So small grains have a short stopping time, and so coupled to the gas extremely quickly. And you can see that drag force will be less efficient for larger grains. And this leads to the second challenge for planet formation, which is radial drift. The drag force will drive particles towards regions of highest pressure. So for a smooth disk, this will often result in inward migration as a pressure is declining smoothly. And the effect of radial drift is maximum for Stokes of around 1, which for the disks in this simulation are between centimeter to a meter sized grains. And this radial drift can happen at very short time scales, much less than the lifetime of the disk, so it means planet formation must happen quite fast. There's one more useful item to introduce for the simulations here, and that is the velocity dispersion of the dust. It's defined by the equation here below, and it'll be used to measure how gravitationally unstable a disk is, as the dust in simulations have no internal energy, so we need a substitute for the sound speed. And it will also be used to compare with the gas sound speed. So for example, if both are identical, then the dust is very well coupled to the gas, as they can be thought of as a single fluid. So there has been some previous work which has looked at the dust dynamics in gravitational stable disks, and these range from 2D and 3D global simulations, which have shown that you can form gravitationally bound clumps in these disks. And there's also been both 2D and 3D local shearing box simulations, which have shown that that the dust of various grain sizes from small to large, so from Stokes of 0.01 all the way to Stokes of 1000, can trace the gas particles, albeit to varying extents. And if this talk is not enough on dust in GI disk, you can also check out Christiana's talk on Thursday. So the main aim here is to explore what drives the dust dynamics, as from the previous works I mentioned, it was not clear which was more important, the drag force or gravity. So for all simulations in this work, we'll be using a disk to star mass ratio of 0.2, and I'll just mention how the disk is set up. So we start by evolving a gas-only disk until the disk becomes gravitationally stable and forms spiral structures, and this is to just get rid of any initial conditions, any artifacts from the initial conditions. So at this point, after 4 outer orbits, after spirals are formed, we add 50 centimeter size dust grains with an initial dust to gas mass ratio of 0.01, and this corresponds to a Stokes of approximately 4, and the dust is added in a manner that matches the gas profile at t equals 0 identically. So this video here shows the evolution of the 50 centimeter size grains. So the dust is immediately attracted to the gas pulse. With a Stokes number of approximately 4, the dust is in a regime where you would normally expect it to be quite decoupled from the gas, especially for non-self-gravitating disks. However, here the dust still traces the spiral structures quite well and eventually forms clumps. So, as you saw from the last few slides, a gravitationally unstable disk is not a smooth disk. The gas spirals are regions of pressure maxima where the dust will drift towards, and this is most easily seen like over here, where you can see that the dust drifts both inwards and outwards depending on its location relative to the spirals. So unlike a smooth disk, the dust does not drift purely inwards, so it's a bit speculative as we can only simulate for one outer orbit here, but perhaps gravitational stabilities are a way to slow down the later drift of dust towards the central star. To understand why the dust forms clumps, as that can be a bit surprising given that the dust was only 1% of the gas, so how could it become gravitationally unstable? So from left to right, it plots the dust to gas mass ratio on the disk, the velocity dispersion compared to the gas sound speed, and the tumor Q. So as the dust, so consequence of the dust drifting inwards is dust drifting towards the gas spirals is that in the spirals the dust density is enhanced by around a factor of 10. The velocity dispersion is also about a third of the gas sound speed. The combination of the two, if you remember the equation for tumor Q, which is also on the top right, is that a lower value for CS and a higher surface density means that in the spirals, the dust disk is unstable, as you can see by the Z regions, where Q is less than 1.7. So that was the reference simulations which all feature simulations will be compared to. And so we start by looking at the role of drag using different size grains, and the grains range from 50 centimeters to 150 centimeters to 500, and finally 5,000 centimeters, and this corresponds to Stokes of about 4, 12, 40, and 400. And shown on the left is the gas density, and on the right is the dust densities for each of the 4 simulations. So in general, it confirms the trends from the shading box simulations, where as the drag force is weaker for increasing dust sizes, we see that the dust is less and less coupled to the gas, and the spirals get weaker. To help understand why, we turn to the velocity dispersion of the dust, which is shown on the left. So on the left, it's the probability density function for the velocity dispersion for one of the simulations on the right. So right now it's for on the right we can see it for the smallest grain sizes, which is for 50 centimeters, and we see that from the white line, the peak of the velocity dispersion of the dust is smaller compared to the gas sound speed, and has a broad tail that extends towards very low velocity dispersion, which aids dust becoming trapped into thin filaments in the spirals and eventually forming bound clumps. Going up to the next grain size, which is 150 centimeters, we see that the peak of the dust velocity dispersion now is approximately similar to the gas sound speed. So as I mentioned earlier, this means that the dust and gas can be thought of as a single fluid, and we see that in a simulation where the dust is very well coupled to the gas, with the widths of the dust spirals matching the gas spirals quite well. Going up in grain size again, we now see that the peak of the velocity dispersion now is now higher than the gas sound speed, and we see the dust starting to become decoupled from the gas, particularly in the outermost parts of the disk where the Stokes numbers are higher. And finally, going up to the largest grain size, almost all the dust particles have a velocity dispersion higher than the gas sound speed. So the dust motion is pretty much uncorrelated to the gas, so we don't really see much spirals, so it is faint. So from these simulations, we clearly see that the drag force is important even for large dust grains with Stokes bigger than unity. However, what it doesn't tell us is how important is gravity, or whether the coupling we saw earlier is purely due to drag. So to investigate the role of gravity, we'll be looking at another 4 simulations where we turn off individual physics one at a time. And so the 4 simulations are, first it's just with full physics, so it's just the normal simulation that's continued further as a comparison. The second is where we turn off the self-gravity of the dust, so the dust does not feel other dust particles. The third, the dust stops feeling the gravity of gas as well, although the gas still feels gas self-gravity. So in that simulation, it pretty much only feels a drag. And finally, it's a simulation where drag is is turned off and it feels the gravity of both gas and dust. In math form, so the dust motion is governed by these four terms, where from left to right it's a drag force, the accelerations from the gas onto the dust, the acceleration from the dust, from other dust onto dust, to the dust self-gravity, and the acceleration of the central star on the dust. So with the full physics, it was all four terms. When dust self-gravity is turned off, A self-grav is not included it's not considered anymore. When the dust only feels drag, the middle two terms are not considered. And when the dust only feels the gravity of gas and dust, we don't include the drag term. So in all four simulations, the only constant is the accelerations from the star. And once again, we'll look at the velocity dispersion to understand what's happening. So in the full physics simulation, as nothing has changed, you still get clumps, as one would expect, by not changing anything. So when the dust self-gravity is turned off, there's not much changes in the velocity dispersion, except for a little bit here in the lower values, which affects the clumps, and how they're affected will be mentioned in some slides later. When the dust can't feel the gas gravity either, we start seeing a lot more differences. So so now there's an increase in the velocity dispersion of the dust, and since it's still smaller than the gas sound speed, the dust still remains in thin filaments. However, it doesn't place the gas parts anymore, and so why is that? So if you recall from earlier that the Stokes number of the dust, the Stokes number is a ratio of the stopping time compared to the orbital time scales, and for the dust here, the Stokes number is 4, so it takes a few orbits for the dust velocities to decay to the gas velocities. So the reason you can't place the gas pulse anymore is simply because the gas pulse keep moving around much faster than the drag force can keep up. And when the dust only feels the gravity of the gas and dust, the velocity dispersion of the dust increases by a lot. It's now much higher than it's now higher than the gas sound speed. So the dust pretty much it decouples from the gas, as you can see here. And although it looks like there's still some spirals left, that's just because it's an early snapshot in time. Eventually, the lack of drag ends up in a very smooth disk with no hints of any spirals. So essentially, the main takeaway is that both gravity and drag is necessary for dust to become trapped in the spirals and place the spiral structures. And neither on their own is enough. So now, as we form clumps, which is important for planet formation, we have a look at how the different physics affected a clump formation. So starting with the full physics, the important thing to note here is that clumps can form extremely quickly. So within half an orbit, about 40% of the dust was in clumps, and after that, clump formation slowed down as there was not much dust left to fall into clumps. So when we turn off the dust self-gravity, it looks like the amount of mass, it looks like it hasn't affected a clump formation much, as the amount of mass in clumps is still the same, but the effect is on the clump mass itself, which I will show in the next slide. But for now, moving on then to when we turn off drag, we can once again highlight the importance of drag on dust trapping in spirals and clumping, as it shows that in the absence of drag, the clumps fall apart almost as fast as they are formed. So this plot here shows a histogram of the clump masses at the final snapshot. So with full physics, we can see that at least half of the clumps are between 1 to 3 Earth masses, but there are a few clumps which are larger than 8 to 10 Earth masses, which is the threshold for runaway accretion to occur. And when the dust can't feel gravity anymore, the effect on clump formation is that a lot of the higher mass clumps break apart into smaller clumps. As you can see, it now peaks at the smallest bin size, and for masses below that, we can't dissolve the clumps anymore. And when dust can't feel any drag, almost all the clumps have broken apart. So the implications for planet formation, as I mentioned, it can create between 1 to 28 mass clumps extremely fast in half an orbit, which can then undergo a runaway accretion to form giant planets at a time scale that could potentially explain some of the very young disks with ring and gap structure that could be from planets. And finally, the dust, due to the presence of gravitational instabilities, does not drift primarily inwards, so it could prolong the disk lifetime, given planet formation much longer to occur. So yeah, so the main conclusion from this work is that the gas piles are able to efficiently trap dust, and for Stokes numbers near unity, the dust can become gravitationally stable to form clumps, and these clumps are in the 1 to 3 Earth mass range, with a few above 10 Earths. And finally, both drag and gravity are necessary to trap dust in the gas piles. Thanks.
Wonderful talk. So just I have a question in the when you put the histograms.
Yeah.
Yeah. So I noticed that after in the first 2, maybe 3 panels, I see a double, like a second peak around 5 and around the 5 in maximum clump.
Yeah.
Is there's an explanation for that, or is that a stochastic effect?
To be honest, I hadn't seen that, so thanks for bringing that to my attention. I don't really have an explanation for that at the moment.
I'm a little bit concerned about two things. So one from experience when I was doing dust and gas simulations, two fluid simulations with my work on RS-48 a few years ago. One issue I found was that even in that case, you could artificially form clumps in the dust, and these clumps arise purely because the dust particles get trapped under the gas smoothing length. So effectively, every single gas particle, so every single dust particle feels the same force from the gas. But in reality, there's going to be some underlying turbulence which is going to cause some diffusion, some kicks in velocity that aren't being captured here, because they're below the gas smoothing length.
Sorry. So
phrase a similar question to be productive, but have you considered this in your simulations?
So the one thing we checked is just to see if we would even expect the dust to become unstable enough to form clumps, and it does satisfy those conditions, but we didn't check against the gas smoothing lengths. Right? If I remember, I think Cristiano might have done that, and it did satisfy those conditions in his simulations as well, which are not too different from mine.
Okay. My other query was, you pick like a single dust size and then assume a 1% mass ratio to the gas, but like there's going to be some mass distribution. Do you have any idea like what kind of would be the global dust to gas ratio, if assuming in your simulations, say like you have like a slope of negative 3.5 with size distribution, how much mass would be in the dust overall in these simulations? And I guess the further question is, if you use like say a much lower dust mass that might be more reflective of at least the crude dust size models that are assumed in most simulations, do you still?
Yeah. So I did do a simulation with all four dust sizes in the simulation at the same time with the s to the minus 3.5 power law, and it does become harder to form clumps if the majority of the dust mass is not in the dust size which has Stokes near unity. So you do need enough of the light a dust size to become unstable enough to form clumps. So say for this simulation, if with the Stokes of about 4, if there was not enough dust mass, or the dust mass was lower, it would be harder for it to become unstable and form clumps.
Okay, thank you.
So I was just wondering, so you've done this experiment all with the gas being gravitationally unstable,
Yeah.
and then the dust on top of that. But what about the situation where the gas is stable and the dust settles to the midplane? Is it possible that the drag could destabilize the dust disk, or the dust could just settle to a thin enough layer that would become gravitationally unstable, even if the gas was stable?
I'm not sure. Again, looking at these plots here, the dust only became unstable because there was an enhancement in the dust to gas mass ratios. So maybe there's something similar, something else that caused enhancements in the dust to gas mass ratio in a stable disk.
Probably like settle, for example. If you make it thin enough, you can make the local dust to gas ratio much higher. I just wondered if you tried anything with self-gravity in a disk which is stable in the gas, and just seeing the dust settle, if anything interesting happens.
The closest to where I see similar clumps is in a completely random simulation with a 0.01 stable, a solar mass disk which was stable, which had a planet which formed links and gaps, and I would see clumps forming around cooling. But there were mistakes in the simulation in the fact that I included a beta cooling in the simulations and forgot that lack of gas gravitational instabilities mean it would just keep on cooling. So it was a very covalent in this, so probably not a realistic simulation. But you could see clumps in that and forming in that.
Okay, I think we'll leave it there. Let's thank Sahl.